certified within 3 years, and it actually defines what it means to be a collaborative. So definitely when you have like an industrial robot or something, it's either caged and you're working from outside, or it's always a safety issue. This actually means where you're pretty much, you can touch and do interaction and collaboration. So this is a collaborative, and it automates like hell, and it's like a collaborative automation. So what are we gonna discuss? Industrial robots and how they came up. What is Baxter? Features of Baxter. Baxter has different configurations. So we are gonna look into different configurations, and then how do we talk to communicate in Baxter? So this different configurations have different way of communication. So we are gonna like discuss the signals and PLC communication. It uses a Modbus TCP format or standard, and we are going to also talk about the research configuration and some of the drawbacks and future scope of this robot. So this was started as an industrial robot, and later it became an research robot. And like I said, it is very much a collaborative robot, and it can work with other robots. So I myself have used Baxter with Motorman, and the level of collaboration is like almost to the touch level. So I'm not going into defining all this. And so we all know it started with the industrial robot started with on very early, it's like 1937, and it slowly went through all these stages, and now we have like the motormans and the arms, which are having like 6 degrees of freedoms, and it can work really fast and quick, and the accuracy is to 0.001 or 9 decimals. And so moving on quickly to Baxter. So what is Baxter? Baxter is 14 degrees of freedom, 7 degrees on each arm, and so it is a 14 degrees of freedom robot with pretty tall. It's taller than me. It's 6 feet 3 inches. So this is a stand which can be manipulated up and down. So the highest it can go like 6 feet 3 inches, and it weighs around 165 pounds to 305 pounds, which makes it really a big robot. It has a max payload of 5 pounds and a gripping torque of 10 pounds. It is a very fast robot, and it uses all sorts of new technologies like Core i7 Intel processor. So it has a back hub. The hub is having a CPU. The CPU is connected to a JCB, which is at the torso. So they communicate using Modbus and RTUs within them. It is fast, and that is why it is having a SSD, and the SSD can be used to make images or porting data sometimes, and this is having a 4 GB RAM. It also has so the Baxter, you can see, I don't know if you can see let me take them. Okay. So the Baxter, the head, it has like a camera, and that has a resolution. It's an HD camera, and it has a resolution of 1280 into 800 pixels, and it also has cameras, the effectors, which I cannot show you in this picture. It has at this surface, at this point, it has cameras over there. So it has cameras at hands, and it has a camera at head. So it gives the field of view completely, and it also gives this closed level of views. These cameras are not so good. This is the HD camera generally. So it requires a 120 volts of power supply, and the operating, they use a different, Rethink Robotics started with a very different operating system. It's called the Intera. They are presently using an Intera of 3.2, which came up last month, and also for the research configuration they use ROS, which is a robot operating system. And what is the basic application? It can do kitting of like packaging, loading and unloading, and machine tending. So I'll just show you a small application. And how do I switch? That is not the Baxter. So it's like one of the application where it is, so this has all these end effectors. These end effectors can be ordered from the company, and it can be designed as according to your applications. And this has like all this, so this is generally a kitting application where it's like picking up stuffs and putting back into packaging, and it can go on forever.
It's funny, it's moving its eyes as if it's looking. The eyes move from tracking the arm.
Yeah. So going back to this.
There it is.
So, what makes Baxter so collaborative, easy to use, and safe? And what makes it different? It has some of the really good features. One is it is using series elastic actuators. I have only heard Universal Robotics using in its UR5 Universal 5 and 6 at this moment these actuators. So what is the use of the actuator? As you can see, there's a series elasticity. So it takes up all the shock, it absorbs the shock, and it doesn't, there is no jerk while moving all these arms. And the entire arm, when you see this whole arm, it has at this point there is like a 0G point, that is called the zero gravity point. When you hold this, it's very mobile, it just moves like a wave. But generally the hand is very stable and it doesn't move at all if you push it back and forth. And this series actuators, how it helps is like, if you're on the way, suddenly there is a hand movement, and if you're on the way, it hits you and stops there. It doesn't hit you, it just comes and does its auto brakes. It applies the brake systems and takes all the shocks and stops over there. It has the software, the Intera helps, like, it has the safety features, like some of the software control, like slow and stop motions and all. This robot also has like an inbuilt human presence detection. So whenever you are within its workspace, it pretty much like, so it has eyes. So you are generally like in a sleep mode. When you are in front of it, it awakes and it automatically detects, but however it doesn't do any kind of movement, but it has that human presence. Personal space, so 360-degree of sonar ring defines its workspace, so that again makes it very, very safe. You see the top ring where it's like at the head, which is like a green ring, and that's like a ring of sonars. It has a range of 4 to 40 centimeters. So within 40 centimeters and all, it again prevents any accidents and also saves the like sudden falling of any other items within that environment. So it immediately stops. So the reaction or the feedback system is very fast.
40 centimeters?
Yes.
That's as far as it can see?
So that's
the human presence detection is about that far? I mean, it looked like the arms were out beyond that.
yeah. So that
Is that 400 centimeters?
no, that's 40. The workspace, we are only considering accidents within very close interface, and that sonars is actually like deactivated in case of an industrial robot. It only comes into feature when it goes to a research application. So when it comes to research application, the applications are generally limited by 40 centimeters. For industrial robots, the head camera and the sonar rings has been deactivated, and as far as I have heard, there were some kind of industrial issues according to US laws, and that's why they have to deactivate that.
Arunava, your slide says that the infrared sensors have a 40 centimeter range. Would it be possible that the ultrasonics have a different range?
No. So then it comes to that, it has a heartbeat signal inside. So they have just renamed it as a heartbeat signal. It's like an emergency signal, and it is like so the Intera software has this signal passed into as like an immediate stop or an emergency stop when there is like again this gives that safety issues. And if you're within this object or within the arms and there is a collide with the arms, this signal is triggered. When this signal is triggered, the engage brakes. After the engage brakes, the motor speeds come to halt, and the robot comes to a stationary mode. As soon as you come out of that area, it goes back into motion. But if you are staying for too long within that region of collision, the robot comes into a confusion mode, and it stops over there unless it's restarted. And it also has padding in its key. So each and every joints, you can see it has padding inside. So all these folds and all, the shocks and shocks are absorbed by the padding. The black circles over there, those are actually the series elastic actuators. So the springs over there keeps taking feedback and helps the system to avoid accidents. So like I said, it has two configurations. One is the industrial and another is the research Baxter. And so in industrial Baxter, how do you communicate this to this Baxter? It's like it has two kind of level of communication. One is between the task internally, and also between the human and the tasks externally. So what is an internal? So let me first tell you what is a task in Baxter. So Baxter is generally very easy to use, and this robot was generally made for people who are not programmer specialists, or like they were made for like almost people who have just come out from high school or something like that, and very grassroots level workers. So now the training is generally through demonstration or holding the hand. So the ZOG point, when you hold and put from one point to the other, you show it and you just save the task, and the task become your like the daily operations. So this task can be further divided into subtasks and actions inside the whole task. So when you start a task first time, there will be like 2 pointers. This is your left arm, this is your right. So this is as a whole called task. This task is when it comes to like you start moving this point to some other point and then store this point and all. This task is further divided into subtasks. which is further divided into actions. Each and every level can be triggered using the signals, and so there might be a point that so for example, if I'm going to move this duster from this point to this point, and after it moves here, I want to bring this chalk from here, I keep it on this, and again move back. So I can define this arm position as like one of the action, and then this as then put a signal over there, trigger this arm, come back here, and then move back. So all this, this is a subtask, this is a subtask, and this is a subtask. The task further is divided into action, which is moving like this. And so there are like, these are the internal signals like ready, error, pause, skip. So this is like one subtask. I trigger a ready signal, and this arm comes back. So then after that, there is a done signal, which is like an output. So after the entire task is done, I can like trigger a done signal and add some more subtasks to it. Maybe move a chair. So like each and every task can take so long, and they divide it into this subtask using these signals. Now, what happens? There are sometimes points where you need to use a PLC. There are like tasks which is huge, like lot of movements, like in a factory or industry where you're maybe using this robot to assemble things. You have so many movements, so many timing diagrams and all. That time you need a PLC. And talking with this robot, generally the company prescribes using click PLCs. However, click PLCs aren't so efficient as compared to Allen Bradley PLCs, which are like very, very industrial standard. So the company did not know how to use Allen Bradley PLCs, and while I was working on this, we figured out with the company, and there are like some basic key points if ever anyone wants to use it, use this robot using a PLC is, first of all, this robot never only takes Boolean signals from the external PLCs. It doesn't take any kind of other instructions but just Boolean signals. And this was actually programmed using Connected Computers Workbench, and it's like a CCD programming, and it's a ladder logic. So what this robot needs is, it always needs an output with respect to an input. So if there are like 3 inputs, it needs 3 outputs. So an input is coupled with an output always. If you don't have enough outputs, it will be in a confusion state, and that I will look for an I/O. So basically there are like no outputs. The robot doesn't do, like the robot doesn't give back any output. It just performs the action. However, but still, there needs to be an output, and that's what the company figured out after we set them. Yeah, that is what. So that is the mapping. In the mapping, always it should be remembered that the input should be given, input address should be given with a 0. So sub 1, 2, and 4 are my inputs. So inputs are basically from my inputs to my PLCs. These are coming from maybe the sensors or conveyors or assembly systems, however, and the outputs are going from the output channels and reaching these DB15 connectors. So external signal is performed via open logic ports in one integrated DB15 connector. So it has a DB15 connector coming out of the robot, and all these PLCs can be attached to that and used and communicated. And also there is emergency stop button coming up with this robot, and that is like a stopper. At any point there is any problem, that e-stop can be used for safety purposes of this robot. So there can be internal signal segmentations. So there can like two arms can be divided. So the entire task doesn't need to be a whole task. Each and every arm task can be divided and segmented, and they can be timed as well. So after moving like this, and then if you need a hold of 5 seconds and then move this arm, you can perform that operation using a PLC or maybe an internal signals. I believe an internal signal will be a more ideal case. So I'll just like to show an example. This was like submitted for a video challenge organized by Rethink like a few days back, and they wanted to see what we can do with this robot, and it was like throughout the world, and also it was a way of spreading the word about this robot. So what we did was actually made robots using this robot, and which sounds kind of like a Terminator movie. However, so what we tried to model was in a conveyor system, when you have like a raw material and there are like lot of workers working, where there is many parts where you're welding, putting back, then assembling, then packaging and all this. So we removed all these workers and used only robots. So we had 2 Baxters and 1 motorman in this entire conveyor. We had PLCs to talk on it, and we actually made it into the top 10 throughout the world. So I'll just show you the video, how it looks like a competition video. So this was done with Industrial Department of NCSU, and this is what we did. So we had 3, these are called MOS robots, and just before I go ahead, yeah, those pieces were MOS robots. They are from the modular robotics. Those pieces, when you like put together, they itself become a functioning robot. So we actually took them as like a toy, and it was like a manufacturing of toy till the packaging. So as you saw, so we had like 3 kinds of robots. So every time we had like 3 designs. So there was a pallet coming in. So all these pallets, each and every pallet has a different design, and so you see this. There are like the 2 Baxters, which are, one is for assembling and the other is for the packaging. And there is this places where the metal balls are coming, and the motorman is putting all the metal balls, and these sensors are attached to this conveyor systems, and the PLCs are using those inputs and putting them into the Baxter as an indication that now this is the task that you have to do. So you can see the accuracy is really not really good, and they are really small cubes. They are almost like a 1 inch by 1 inch cubes. And so after the assembly, so now that's like a functioning card. And And it also has a suction cube and it's placed ready. So yeah. So that was like a very good example of what you can, all the functions that you can do with this robot. And after this, I'll be moving on to the research configuration. So before that, if you have any questions with this industrial robot or the industrial configuration of this robot.
When it was doing the assembly, did the sensors verify that when it reached to pick up each piece that it detected the piece was there?
Yes. So, okay, we had this palette with all the pieces, and the Baxter was already programmed to which are the pieces it takes. So the sensors were not triggering whether the pieces were present, but the sensors were, instead of triggering, they were like metal plates, and each and every metal plate represented a design itself. And so whenever there was a design one, the Baxter knew where are the pieces, and the pieces, like we put the pieces according to the design one.
If a piece was missing, would it still keep going with the rest of the process?
That can be prevented using a research robot or maybe a vision system, but not this one.
Okay, the sensors can't detect that it actually grabs something when it goes to grab?
So it will go and it will try grabbing once, it will fail, and again it will try. After 2 times it will give the system will stop, and
So the compliance there is simply mechanical. I thought that perhaps that was a sensor value that was available to the control system.
So in case if I'm using, I think you can do the sensing using the camera present in the hand, but we did not use that. Anything else?
What kind of, you said there were sort of small pieces, and they did seem to get very, move to very precise placement, but how precise can you place something? Precisely, I guess.
It actually talks about the drawbacks. So the Baxter has some offset. It has sometimes the offset goes almost like 2.5 millimeters, and many times, sometimes it fails. But like you saw, those pieces are really like 1 inches, really small pieces. And if one of those metal balls is knocked over, the entire connection fails. So for this operation, this video is generally like a combination of some of the failures and passes. However, like we did some of the runs where it could go all through, and sometimes it never happened. So the robot is not always predictable. Sometimes it fails to do the same thing, but after like maybe just a restart, it might do that. So it can go really precise, but so the series actuators present, there is an auto calibration feature to the robot. So if you extend the arm and keep it like that, after every 2 or 3 seconds you will see the hand is just moving. So it is every time calibrating itself and moving the torque sensing feature into like position. So this advantage actually works as a disadvantage when it comes to really precise things, and sometimes it fails when it comes to very high precisions.
How long does it take to set up Baxter to do a task that complex?
That task took us 3 months.
3 months?
Yes. However, like that is like a very precise joints. Generally, like in industries, like I showed you the kitting or the first video where they were like putting bison on. It's just like they're big objects, so it's like move the arm, put it there, done. It hardly takes like 5 minutes to teach the robot to do what you have to. But this is like a special case.
So the actual Baxter movements in your video there took a week or so to program?
3 months.
The actual movements of the Baxter only, not the whole system, but just when the plate stopped in front of the Baxter and it started moving parts, that took about a week or so, you said, to program?
Yes,
Okay.
that the entire thing actually, like the whole process, the first part was like the communication. Neither the company knew or neither we knew how to communicate with the Baxter. So after that, it took another 1.5 months to position and program all these things. So 1.5 months for communication, 1.5 months for the program. Yes.
With those magnetic blocks, did you get any errors due to them snapping into place, or did it make it easier to program since you could maybe get it close and have it still?
So as Baxter's body is made of plastic and the outer coverings and all, so it doesn't matter whether I'm dealing with metals or what it doesn't matter with the material of the.
Okay, but he didn't, or the sensors didn't feel the block, like it pulled into place and trip any type of.
So as they are like really small blocks, there was every time there was a high chance of knocking out those small balls which are like so small. So if I see the Baxter gripper, it's almost like this fat. If it moves almost, if there is an error of almost like a millimeter, it will knock the ball off. So there is like an 1 inch and that much of space, so there is not enough space to make errors. But yeah, that's what. We had time and again the balls were flying off.
So what would happen? What would happen with the Baxter when error did happen? I mean, something got knocked off and it realized it.
So, are you talking about this application?
But yours, yeah.
Okay, for my application, each and every block had 8 joints. So even if a metal falls off, it doesn't make a lot of difference. However, to make it completely perfect, so your question is like, what will happen if a ball actually knocks off? The Baxter will never know, because I'm not doing any kind of image detection. I'm just picking that thing and putting it together. And that's what. If the ball falls, it might fail. If it cannot join it properly, after some time it will go into confusion state and the system will stop. Okay, so then it comes to the research Baxter. So it is like an industrially tested automation solution which is embedded with embedded features and open source ROS API, and that's what makes research Baxter. So all the like drawbacks or limitations and everything, every like hurdle you face in an industrial robot, like I had problems with the arm several times where I cannot like access every joints. Sometimes there were problems I could not segment the tasks properly, or I really wish if I could access the head camera, which is visible for the industrial system, and that all these like limitations of industrial system can be overcome using the research robot, and the research robot actually enables you each and every feature of that robot. So what is the good thing about the research robot is, like first thing I must say about this robot is nothing is proprietary. Nothing is like this thing belongs to Rethink and you cannot use this. Everything is open source. Even the back CPU is just like a Dell. It's a Dell CPU with all the like normal hardwares you have in a computer or a desktop system, and everything is open source. Even the hardware, I don't know about the JCB within the torso, which is like we cannot open that. I don't know about that. However, like everything is open source. So the advantages of this robot is like it has all the URDFs, which is like the C++ or sometimes also Python libraries, which are everything is available, and it has access to all the 14 arm joints. So I said in industrial robot there were sometimes you cannot access all the joints, but here you can manipulate each and every small joints within the entire arm. It has you can control the position, the velocity, and also the force sensing of this robot using the research configuration, and that is pretty much hardcode coding. So it is not when it comes to the research robot, it is no more holding the 0G point and just training and placing it at one point. So and next, as it uses ROS. The ROS community is open source always, and it has all the open source features like RVs and MoveIt. MoveIt is generally a motion planning interface when it comes to the robot operating platform, and okay, so it is easy to communicate with the Baxter online forum and other researchers. So when you actually open up this research robot, you don't need to worry whether you don't need to know a lot about the ROS, or you don't need to know everything about this thing. There is samples for everything you want to do with this robot. And also there are like Google groups which where the company professionals itself sit, and they keep responding and helping you within throughout the 24 hours, and they are always active. And the good thing about Rethink is like their support and help is very fast, within like days and all, and they send you everything. If there is a problem, a small problem, they just replace the whole system and send you within a overnight shipping. So the research Baxter also support 3D simulator environment, and which is generally like a Baxter has a gazebo, and also it has the like I said, the MoveIt framework. So what actually the MoveIt framework does is sometimes you might not know programming a lot, like moving this into the mechanics and then arms and putting it back. So what does a MoveIt does is now MoveIt generally like it's like a GUI where you can just in the Baxter MoveIt you can just point the places you wanna do the task, and if suppose you have an object or like a obstacle, you can pretty much like describe it in your MoveIt using the object models which are available on the site. I really wish if I can access that. Yeah, so as it comes to so this is a Linux terminal, and if I go ahead and show you actually what it does. So you can see he can control each and every dynamics of this arm, and this is a GUI, and he's not doing any kind of programming over there. However, like it is also open to programming and Python scripts mainly. So here he is describing value on the arm, and this simulator, if you so this is all the manipulation he did, And after that, this can just, so he just pretty much actually took all those things, moved the point and come back and saved those, and the system just got programmed itself, and you can do it remotely from any point. So I don't know whether it has shown the obstacle. Yeah. So this obstacle, so he loads a model. So these were the scripts I was saying. He loads a model, and so he creates an environment as he has, and then he just goes programming it. And then this robot never hits the box, it just goes away, turn around and comes back. So all these things he just do and like sit and do it in a GUI without doing much of programming. So even the research configuration isn't like too much of programming. If I come back.
Can you manually move the arm and save points and have it?
That's what you are doing. That's what you are doing in case of industrial robot.
How? I was going to ask
please.
a question, but go ahead and finish.
Please.
I was just wondering truly how replaceable one of the robots was on your line if, like one had been accidentally knocked over by someone and smashed beyond repair. How simple would it have been just to get another Baxter? I mean, obviously after all the crying and everything else was done, but to replace it, and how easy is it just to replace one of the Baxters?
In other words, can you save the program and use it on a different machine?
I guess I was assuming that, but yeah. So is the
Calibration.
program for a Baxter unique, for any one Baxter unique, or is you just save it, bring in a Baxter, and run it?
Okay. So first question you asked was how easy it is to replace it, and this was all the dealing is done by the university. However, I just know if there are like small problems, I had some booting up problems with the CPU, and they I just sent them a problem, and they just looked at the log files, and they immediately sent me a new CPU without even they don't care whether you send it back or not, and it's like overnight happened. So that makes me believe that even when it comes to damage or beyond repair stuff, it won't be a lot of headache. Next is whether your program to Baxter is unique or not. So do you mean your program to one Baxter is unique to that Baxter, and you want to use that program into another Baxter? Because Baxter program is always unique to Baxter, but if you are thinking of using the same program in another Baxter, you can do that.
Okay.
So there are USB devices, and all these tasks get saved. So you can just put the USB, copy the thing, put it into another thing, and it is possible. And there is also a task editor of this robot, which actually increases the features or the functionality of the research robot. So what does a task editor does is it controls the acceleration, force, torque, all these small dynamics and the components of your movement or the robot, and that can be accessed using the IP, and there is a way of going into, and it can be done remotely. So I can, being in NCSU network, I can access my Baxter, which is miles away from my lab, and I can still make changes to its all its components and whatever dynamics I wish to. So yeah. piece.
Is the safety features always running, so even when he was doing his thing, if you went up there and got in its way, it would?
Always. Even, yeah, it is always like, always active.
What was your question?
Yes, sir.
If the safety features are always running, even when it's in research mode, and you tell it.
I worked with industrial robots years ago, and a lot of management required us to put in, like, for instance, laser safety shields, where if you interrupt the beam, you would disable the robots. And these are robots, I assume Baxter, if unguarded by software, could punch you and kill you. Do you agree that it has the force in its actuators in order to do that?
No, it's designed, I mean, it's advertised as the safest robot.
Yes.
The force control, basically, it doesn't produce more than, what, you said 10 pounds of pressure?
Okay, it's a matter of mass and acceleration, though. If you get an arm moving after a while, it's got a certain momentum. It's gonna. I mean, I've seen a Scara robot, which is IBM's arm, 30 years ago. Basically, just a 3-axis with an end effector, Z-axis, punch basically some rails and knock the Lexan sheets out of the rails and knock the 2 steel rails to the ground, bending the bolt, breaking the bolts that were holding it. So, I mean, these robots, even small robots, have a lot of punch to them. I don't know whether Baxter how it's disabled, in terms of its actuators when it comes into contact with something it's not expecting its work cell. But if it's all software, then, software has failures. So,
Yeah.
I'm just wondering about the safety aspect and, to what extent it's hardware interlocked to prevent killing somebody, if it's in fact even capable of doing that.
Okay, so, like if I go into details with the safety, it's like almost like 3 to 4 pages. However, Baxter does safety is just not on software level, so it's also on the hardware level. So, like I said about the actuators and the elastic actuators, so it doesn't. So whenever it is actually experiencing some kind of obstacle, the sensors are working, and as it has its own operating system, it doesn't have the it's not like a software which is controlling some of the features of the robots. It is like an entire OS along with the hardware features, which is also coupled with safety. But like you said, like a software failure, I cannot imagine of such a situation because it hasn't happened so far. And I don't think it can happen like that because it is like always vigilant with that. Yes, sir.
It's a purposely very slow robot.
But when you actually come to the point, if you go back to my example where I showed you the video, was putting up the pieces and all, it's not, you cannot call it slow.
Well, if you've seen industrial robots that are working, they're almost faster than you can see their arms moving.
Yeah.
And the robots he was talking about weighed, I don't know, we had a Puma, and that thing was 5,000 or 6,000 pounds.
Sure.
And still, it could only pick up like 15 pounds, but the inertia of the arm, because it was so heavy, could hurt. But this guy is very lightweight.
Yeah.
Are its arms plastic?
A mouse.
Yes.
The mass of the arms is very low.
Okay.
It moves very slowly. It has elasticity, which makes it a little bit inaccuracy.
Right.
To be able to feel that you've hit something, you've got to have some give in your servo loop. So to have the elasticity, it has to lose the accuracy, because if you put a load on it and you have elasticity, it's going to be off a little bit.
Yeah.
Is that correct?
Yes, sir.
Is it plausible that the software at the lowest level to do with that force sensing, to do with the no, it won't keep going when it's meeting resistance, is not accessible to you, is not open source, and is something that the manufacturer provides? Or do you have control at the lowest level? Could you modify the software and
I'll answer
defeat
it
those
for-
safety features?
Sure. I'll answer it for both the configuration. Because when it comes to both the configuration, everything gets very different. So for the research, for the industrial robot, I said about the task editor, and you can actually control the speed, force, range, for example, range of your IS sensor, or like the acceleration of your arm, speed of your arm, and also I don't remember some of the dynamics, some torque dynamics, some sensing dynamics, everything can be controlled. But I don't know if there is even a deeper level to that, but at least that serves most of the purpose. When it comes to the research robot, it's pretty much like a blank sheet, and you're not doing, nothing is there, you're programming everything over there. So you can control everything in a research robot.
Two more questions. For the research robot, did you have to sign a waiver that said you will not sue the manufacturer for the consequences of using it?
Now the safety doesn't.
Okay. The second question, approximately how expensive is
It is $27,000.
this? 37?
27.
27? Cheap.
Very cheap.
Gosh, I would have guessed a lot.
Now,
Does that include the optional?
is that school's cost or
Yeah,
not?
it's not.
Does that include the optional rolling base? I know they have a standard base and they have a rolling base. I think that's
No, it's $27,000. It's exactly $27,000 for changing the system. For example, we had the industrial robot and we did not buy a separate research. So for changing the system, if you are changing it yourself, it's $500. If you are sending them, getting them everything done, it's $2,000. Okay, and yeah, I just agree with you. The speed with compared to the Motorman, it's way much different. Motorman is like super quick,
Yeah, the Motorman could hurt you.
and it can kill you. So
And you were not operating it at full speed, I don't think.
the Motorman, yes.
You were at full speed with it?
Actually, the Motorman, one of the faculties in IAC did. I did not control the Motorman. He's like an expert in that. I was working with the Baxter and the conveyor PLCs. Okay, so I like this. What you actually do with the research robot, like in an industrial robot, you implement into some of the manufacturing systems and stuffs and all. So these are some of the things you can think of doing with a research robot, or like implement or develop or something. So one of them is like Baxter's robot vision can be programmed to create advanced tools and transform labor-intensive industries. So I've worked with many Baxter's, I've worked with some of the robots, and I have worked with some of the vision systems. And according to me, Baxter's vision system is, when it comes to research and all, it's not so efficient. And the effective resolution at some point is like 640 to 480. I believe a Kinect can be used way much better for doing image processing and stuff. Moreover, it is a 2D camera, and it doesn't fetch you 3D information. So like my thesis is actually like working, pairing of the Kinect with the Baxter and perform 3D depth manipulation and then do real-time handoff and all these things. So that is one of the things that can be performed. Next, it also has like some of the industrial oriented cameras like Cognex and all, which are very expensive. However, if you want to really have like a very large scale industry and there you want to implement that, I think you can use some of the machine vision systems and then pair up with those things and use it for some of your applications. When it comes to Baxter, there is a lot of algorithm development, machine learning, which is basically like comes to the like mathematics level and also like programming and stuff. That can be also done. Pattern recognition, motion planning, and all these things can be developed using Baxter. One thing is that research Baxter is much accurate, more accurate than industrial, because in research you can access all the things. In the industrial, those offsets continue to be there. And human-robot interaction, that is like something that can be really performed with using these robots, because these robots are like so safe to handle. They're really, really so safe to handle that many times I have been on the way and they have just stopped here. I believe some of the interaction can be done, and as the feedback system is pretty fast, and this is, the CPUs and all these processors are pretty fast, it can be done in real time and immediately. And so I've seen some of the visual servoing where they have used a Kinect to imitate these movements, and the person is actually moving and the Baxter is also doing it. Or even sometimes like human and a Baxter is working together. They're like immediate. They don't have to be like a waiting system or a hold system, something like that. So some of the drawbacks that like I mentioned, continuous recalibration, which they actually say as like an advantage, it works as a disadvantage at some point. High offset, not repetitive. Sometimes it fails. It fails without any reason. You just restart the robot and it works. I don't know why. And some of the future scope, it is like widely accepted. Most of the industries are like using it. It also helping many people to get employed. And the application spectrum and features can be made wider, because if you actually go into the task and subtask, all those signaling and things, there are points where you really feel that there are limitations and wish you had access to some of the features that can be self-manipulated and used. Like, for example, there was a huge problem, there was a big problem where I was stuck for some time, was this hand, for example, there is an object. I need come over here and hold the stuff, and then I need this arm to be there. I need this arm to come here, take this and go back. Till then it should be there. So for example, I have a trigger hold signal for this, that you do, I have a trigger signal, triggered, came here, gave a hold signal for 5 seconds. But I have only given the hold signal for this. But this arm also like actually gets subjected to the whole system. And what happens, like 5 seconds, and after that it goes off, and after 5 seconds it comes back. Nothing is there. So those are some of the like these features, timing problems. Well, that was in short about all these Baxters, and I think Charles can put this PPT if you need. You can take it from me. I can mail you, and it has like all the things I've shown you. I have all the hyperlinks, and you can get access to everything. And just Google Baxter and you have everything open. The GitHub, the codes, the samples, everything is over there. So nothing is like they have kept it back of that. That's it. Okay, so
Thank you. If you could send us the slides and the links that you mentioned, I'll go ahead and hopefully if the recording went well, we will post it to YouTube and everyone should be able to view it later if you can.
sure. I'll mail you the this presentation, and all the links are in the references, so it's there.
All right. So we had that survey that I showed you guys earlier.